Let's go over the test. Let's try that again. Problem number 1. You have a 3-phase 15 MVA load that operates at a 0.8 lagging power factor. It's supplied from a 115 kV line. The line impedance is 50 plus J 100 ohms. The first question I asked was find I load, right? And what we talked about in this class is solving for the load. You're going to have a power supply over here that its voltage is adjustable. You're going to have a line here with an impedance, Z line, and then you're going to have the load at the end. This nominal voltage is 115 kV, right? That's a line-to-line voltage, remember? And it's okay to keep it as a 115 kV voltage, but sometimes, especially when you're learning the material, is to immediately convert it to a line to neutral voltage. Yes, sir.
So it asks for line current though. So
Mhm.
you'd use phase voltage to find line current?
Isn't this a series circuit? Isn't line current the same as load current?
Oh, yeah.
It's just a series circuit, right? So that current exists everywhere. So it's line current, it's load current, it's the same thing. Okay. So now we know S for 3-phase is equal to 3V phase times I phase conjugate. If you don't like that one, V load, I load conjugate, or I line conjugate, right? So at this point, I line, which is going to be equal to I phase, is going to be equal to S 3-phase divided by 3 V phase conjugate, right? How do I solve for S 3-phase? I draw a power triangle. This is 15 MVA. This is inverse cosine of 0.85. And this is P and Q. So with that power triangle, you should be able to get S 3-phase. So this is 15 MVA at an inverse cosine of 0.85 times 3 V phase, which is 115K over the square root of 3 at an angle of 0. And then I have to take the conjugate of that whole entire thing. Some people, and I'm not telling you to write this down because you should not do this, but some people said V divided by Z equals I, which they said 115 divided by 115K divided by 50 plus J 100 equals the current. Why is that wrong? Because if you want to solve for the current through something, you have to have the voltage drop across that something, right? Ohm's law says V equals I times Z. So if I want to get I times Z, I'm getting the voltage drop across that element. Are you getting a full 115,000 volts dropped across that line? You better not, right? Because that would mean that the load is getting no voltage. So you really can't use that approach here. You had to use this approach. What is the actual current going to the load? Okay. That's how to do 1A. Should say 1A. Questions on A? Yes, sir.
So, on the answer, the number on the top is the apparent power.
Right here, the 15 MVA.
I'm talking about the answer, the last thing they put in the question.
Right here.
Yeah.
Yep,
So on the numerator, it's the apparent power at an angle, negative, cosine inverse of the power factor, and then what's that bottom value, what is that equal to?
right here.
Yeah.
This right here is 3V phase. Right? Remember the phase voltage we said was 115 kV at an angle of 0. We picked it to be our reference point, so that's why we kept at an angle of 0. And we converted it to a phase voltage by dividing by the square root of 3. So that's where we got that voltage.
We needed an angle as about.
For I,
Yeah.
anybody want to answer that question other than for Wyatt? When we live in AC land, what does voltage and current have? Two parts. What are they? Magnitude and angle. We've mentioned that several times in this class, right? And I even warned you that if you are given, I think it was even during the exam review, I said, if I ask you for the current, you should provide a magnitude and angle. If I ask you for the magnitude of the current or the angle of a current, that's different. But current and voltage always have a magnitude and angle. Very, very important. Yes, sir.
Are you gonna put the answers of that one?
No, you know why? Your chance to do it. If you want to check your work, right, you have the whole thing here. You can go through and do your calculator and come up with the results. If you want to go ahead and do it line by line, that's fine. But I think it's good practice for you to go through the problems. It really helps. Like if I just give you the answers, then you're just going to check your answers and put the test away. But if you want to go the extra step and see what's happening and enter in your calculator, what happens? That's extra learning opportunity. And it's not a homework assignment. It's just an opportunity for you to learn a little bit more. Go ahead.
Remember the angle was negative for this?
Yes, it better be. Why? Why is the angle negative? Aha. And who lags whom? Current lags the voltage. So if the voltage is at an angle of 0, which it is, and if you believe that it's a lagging power factor, should the angle be positive or negative with the voltage angle of 0? Yep.
When you said you have to take the conjugate of it, that was the sign of your angle.
Yeah, because it's a complex conjugate. You see right here, this is a positive angle. Inverse cosine of 0.85 is positive 31.8. When you take the conjugate, you get a negative angle. Make sense? Don't make sense? Yes, sir.
If let's say in the question you're given a voltage with an angle that's positive, and then you're told that the current is lagging, can the current be just lesser positive?
Yeah, as long as, like if I had said this was 80 degrees, yeah, it would just be 80 minus 31.8. That's still a lagging power factor. But we try to simplify things a little bit in this class. We try to make the voltage to be at an angle of 0, especially where it's you're just picking a reference. So most of the time, not all the time, but most of the time, the voltage will be 0. Okay. Any more questions on this one? Part B. I said, what is the line power loss? And I warned you about this too, right? I said, you've got to make sure if you want to get the line power loss, you've got to use the voltage drop across the line or the current through the line to calculate the power loss. That's the first thing I said. You just calculated the line current, right? So let's use I squared times R, not S, but R. I mean, not Z, but R. And I also warned people too, that has to be a magnitude of current. And at the exam review, I said, I don't want to see any powers equal to 7 plus J2. There should be no J terms. Power is a purely scalar number, real power. Reactive power is a scalar number. It's only when you add them together in S do you get a vector. So take the magnitude of I you just calculated, magnitude only, multiply it by the resistance of the line, not the impedance, but the resistance. And you got your answer. Right? But this is P line per phase. How many phases in this line? So if I want to go from single phase to three phase, what do I need to do to P line? Because I have three wires carrying the power. So I have three equivalent 50 plus J 100 ohm impedances in those lines. So I got to multiply that by 3. Questions on part B? Sneaky, tricky? Aaron said yes, sneaky.
Do you put a circuit diagram on the next step? I think that would have I would definitely realize power times 3 thing with a circuit diagram. So. But
Well, how would a circuit diagram? Because a circuit diagram is only a single phase representation, right?
well, then why is it does this they're saying it's 3?
Because it's a single phase representation of a three-phase line. You actually have all three phases, right?
Yeah.
But it's much easier to look at one phase and just know we have two other phases.
It's the same thing.
Yeah, and I'm not being sneaky or mean about it. If you go to industry, you guys worked in industry. What do they call a one-line diagram? Why not call it a three-line diagram? Because you only see one line. You do actually have three-line diagrams, but they're actually more for what they call AC elementary. It's how you actually connect CTs and wires and all that stuff. It's actually, what's that? Yeah, you look at it a lot because you're trying to troubleshoot the wiring, right, to the relays. But if I'm actually trying to understand the power flow, or let me ask you this, if you guys are trying to understand the power flow through a plant, do you ever look at the three line? Yeah, it's got too much, and usually three lines are so much detail, you get lost in all the amount of information. One lines tell you way more information about the flow. So again, I'm not doing that to be sneaky. I'm just telling you, if you work in this industry when you graduate, this is exactly what you're going to see. You can even pick on your partners and blame them. That's just how the industry works. But you'll actually find it's a lot easier to do it that way too. Part C. Power factor of the load. Told you in the problem. You could have just circled it and put an arrow down and gotten 10 points. Wasn't meant to be sneaky, just was like, what's the power factor of the load? Just being able to see if you can interpret what the information is there. Sometimes it seems like it should be harder than it is, but that was not my intention here. That's it for problem 1. Questions on number 1? Everybody's really quiet. Does that mean it's still confusing or?
I did not write the word lagging, and that I think some 10 points and 9 points.
Do you want me to take more points off? I only took 1 point because remember I said power factor has. Well, we'll keep looking through the test. But the idea, right? A power factor, it's very important to know if it's leading or lagging, right? Yeah, because if I tell you if something has a 0.9 power factor, this is the load, is that enough to be able to do any calculations on it? No, you got to know if it's got a lagging angle or a leading angle. If I told you it was capacitive and resistive, that's essentially telling you it's a lagging or leading power factor. But from what I remember, when we were grading your test, I don't remember if you said it was an inductive. And had you said it was an inductive load, I would have probably given you 10 points. I might have given you a hard time saying, why don't you just say lagging? It's easier to say that, but I don't remember seeing that on your test. All right, number 2. So like Aaron pointed out, right? It's sometimes easier to draw a diagram. So why not draw a diagram? We have 3 loads. I mean, 2 3-phase loads. And I said, put those loads in parallel. Is this load, or find the equivalent impedance, which you know they're in parallel with each other, right? In the real world, all of our loads are in parallel, or most of our loads are in parallel. So those loads are in parallel. We want to deliver nominal or rated voltage. Is this load ZY in parallel with Z delta? Meaning they have to have two common nodes. Is this node and this node the same as this node and this node? How about even over here, this node and this node? Well, this one looks good. Check. But let's follow this one through. Oh, I've got another resistor go through. So those aren't in parallel with each other. So you couldn't come up with an equivalent impedance unless you did this. Or, nope, you did this. I can see that this one is definitely in parallel with this one. And over here, is this one in parallel with this one? Are these points electrically at the same point? There's no wire between them, but remember in this class, everything is balanced. So this is at 0 volts and that's at 0 volts. Electrically speaking, they're at the exact same potential, which means they are in parallel. So all you needed to do this one was you were given 1245 delta or 560Y. Convert either one and then put them in parallel. So let's say you want to do the Y connection. So to go from delta to Y, you have to divide by 3. So Z equivalent per phase, at an angle of 45. That was it. You could have done delta. So this is equivalent Y. If you wanted to do delta, this one converts to, we're going to multiply by 3. Yes, sir.
What I'm doing is, the first answer, your Z equivalent with the Y was different from the Z equivalent with the delta.
Absolutely.
So, I don't know, are they not supposed to be the same?
No, they should not be the same because this over here, okay, so here's my Y. If I have a delta, equivalent is I'm looking across those. So this here has to be the equivalent of those. So ZY has to be equal to 1/3 Z delta. Had you divided it by 3 or multiplied by 3, depending which way you go, you would have got the same answer. And you can check that here. If you do these calculations, if you multiply or divide by 3, you'll get the same result.
Also, this question got me confused because it said find the equivalent impedance of the two nodes.
Yep.
Which I thought was the entire three-phase system.
Ah, thank you very much. Zali just had a,
So, like, it was there.
it's an excellent point. He thought it was kind of combining all the three-phase elements, right, into one. Can you do that?
I know you can, but I couldn't remember how.
You can't actually.
It's 3 different phases.
There are 3 different phases. So how would you ever be able to connect? Because remember, these are 3 separate connections. And remember, when I say equivalent impedance, that's a Thevenin equivalent. If I've got a source looking at that over there, how can I add these 2 in here? They're not connected. So there's no such thing as a 3-phase equivalent impedance. There are single-phase equivalent impedances. Each one, you have to have 3 of them to make it work. You can't build the 3-phase resistor. You can build a load that consists of 3 single-phase resistors and connect them as you want, but you still need to have 3 resistors. Go look at cap banks, go look at load banks, go look, you know, when we did the AC machines, when we saw we had coils of wire, we had 3 separate coils of wire that we interconnected at the terminals of the machine to get us what we wanted. But yeah, we don't connect impedances together. So that's a very good point. But what that tells you is like, we need to really understand what the difference is between a 3-phase load and a 3-phase or single-phase resistor. Those are 2 very different entities. 3-phase resistors don't exist. Okay. Any more questions or discussion on number 2? All right, number 3, power triangle time. We'll call it original, S original. You have to do 2 power triangles. And the difference between this value here and here was Q cap. So all you needed to do was build your power triangle. So let's see, we had 15 megawatts. This is the inverse cosine of 0.85. This is still 15 megawatts, but now I want it to be the inverse cosine of 0.95. This is Q original. You all can calculate Q original, right? Just doing trig identities. This is Q new. So Q cap is equal to the original capacitor, the original system, minus the new, because it's going to make up the difference. And that's going to be equal to V squared over X sub C. Here's where some people made a mistake. And it goes back to Nazali's question. Is there such thing as a 3-phase capacitor? No. There is 3 single-phase capacitors connected in Y, or, whoops, let me give myself a little more room. Or in delta, right? And so each capacitor is responsible for 1/3 of the Q cap. The cap bank itself, notice I said cap bank, is responsible for the 3-phase total. Each individual one is responsible for 1/3. So if you did this is okay, but keep in mind, I had to divide that whole thing by 3, right? Because one capacitor is not going to work. Why won't one capacitor work? Because 2 other capacitors are needed to balance out those other phases. Otherwise, you have an unbalanced system. So most people forgot to convert that to a single phase equivalent. And the reason why I showed this, Y or delta, is because this voltage here has to be a phase voltage. You can see across here, you were given 138 kV, but that's across the line. I would have had to divide that by square root of 3. So if you used Y connected one, Q cap was equal to, whoops, I'll just show the numbers. 138K divided by the square root of 3, divided by 3 times X sub C, right? So that's how you could go ahead and get the value there. Or, so this is Y connected, or if it's delta connected, it's just 138. Oops, I forgot to square it. Sorry about that. So you can see that a delta connected cap bank can be a little bit smaller because the voltage across the capacitor is higher. It can do more work. And notice I don't have any angles in there. Why not? Because it's the magnitude of V over X, not V over X. And then the last thing, once you had X sub C, because does everybody know how to solve for X sub C in either of these equations? X sub C is 1 over 2 pi F C. Solve for C. And you get 2 different answers. Yes, sir.
So, say, obviously you forgot it was, didn't think about it being three phase, but if someone was to have said like. One of their caps, like they had just like what the cap should have been and then like, but. Three caps of like say six, like the 600 narrow,
If the answer was 600, but you had to divide by
Yeah,
three.
yeah,
So as long as you divide by three, that's fine.
yeah, okay. So you actually had, so you had to divide that number by.
You had to divide the Q by three, right?
Okay, and then you said three caps of that,
Yes,
okay,
because you don't have a total capacitance. You have three single phase capacitors connected in delta or Y. I'm not trying to be difficult. I'm just trying to,
We've had to get like full credit on, we've had to specify delta or Y to know
right, or make it clear that that's what you were doing. Yes,
that's what you meant to do.
Right.
And you just actually showed up at it,
right.
okay.
Yep. Because you can see it's very different results, right? And why is it important? Because if I order a cap and you connect to delta, but I actually, had it configured for Y, there could be a problem, right? It might not work.
Okay, that was actually a hang up I had on it, because it didn't specify which one, so.
You got to pick
So you got to pick it.
your choice. I accepted either problem. I mean, either answer.
Okay.
Any more questions on number 3? Number 4. Let's draw a circuit. So what is the current from the power supply? What does the current have again? I forgot. Magnitude and angle. So I has to be equal to V divided by Z in this really basic, simple RL circuit. What's R? I mean, what's V? 128 at an angle of 0. We're going to pick it as a reference. What's Z equal to? It's not 2 plus 7 millihenry. Yeah, this is in Henry. If I'm doing AC steady state circuit analysis, I have to convert that to ohms, which means X sub L is going to be equal to 2 pi F L. So I had to multiply that by 377, and I had to multiply that by J. And so when you do that, you end up with 2 plus J 2.64. Oops. And that has a unit of ohms, and that's going to give me a current. Now, a few people, just be aware, a few people, and this is okay, they did this. And then they did this. To get the magnitude and the angle. That's perfectly fine. However, you're going to spend a lot of time this semester and next semester if you do everything calculating it that way. Your calculators, unless you have a really small basic calculator, has no problem calculating that out for you. You should be able to just enter it in exactly. In MATLAB, you can do that piece of cake too. Here's how I would do it in MATLAB. I'll show you how simple it is. If I can find MATLAB. So Z is equal to 2 plus, oops, 2.64 J, right? V is equal to 120 at an angle of 0, which is just 120. So I is equal to V divided by Z, right? That's in rectangular. If I wanted to make it look pretty, in MATLAB, it doesn't work so well. So I have to do the absolute value of I, which is another way to say magnitude, and the angle of I. And then I have to convert this to degrees because that's how MATLAB rolls. I just showed you the actual calculation result. to do number 4. Because a lot of people made this problem much harder to do than otherwise. So with that being said, don't make it harder on yourselves. Use your calculator. Okay, so I'm not criticizing how you were taught before. I'm just showing you that there's a much easier, much more efficient way to do it if you enter it in this way. Okay? Questions on that? No questions? Okay, let's do number 5. Let's do a delta connected. VBC. I said determine the line voltages. What's the line voltage? So the line voltages are as given. 480 at an angle of whatever. What are the phase voltages? It's the same voltage as the line voltage. And the delta, right? Remember that table we put out? Line and phase voltages are exactly the same. So both of those were as shown. And then the phasor diagram. That's it. 15 points. It's a hard problem. Some people tried to multiply by square root of 3. Some people tried to divide by the square root of 3. Just draw a picture. You see with the picture, right? You can see what phase and line voltages are. Any further discussion on number 5? Number 6, had to do open and short circuit tests. So let's see, we had, my sheet is kind of hard to see. So let's see, I have open circuit. This is V, I, and P. Right? And these were both shown on the primary or the high voltage side. So these were both on the high side. So I didn't make you have to do any conversions. So the very first thing we need to do, power triangle. 2400 times 0.2083, 185. You should be able to calculate theta open circuit, right? Open circuit test solved for R sub C and X sub M, right? So Y open circuit is going to be equal to V, not V open circuit, I open circuit divided by B open circuit. Remember, this is at an angle, my brain not working today, at an angle of 0. This is the negative theta open circuit, and that's going to be equal to 1 over RC minus 1 over JXM. To do the short circuit, boy, oh boy, it looks awfully similar. This is 615. This is 52 times 20.83. Find theta short circuit, and Z short circuit is V short circuit at an angle of 0 divided by I short circuit at an angle of negative theta short circuit. And that's equal to R equivalent plus JX equivalent. If you got that far, I probably would have given you full credit. But some people did RS and RP. As long as your approach was reasonable, I gave you credit on it. Yes, sir.
I guess I'll ask you out afterwards why I didn't.
Oh, yeah, if it's, yeah, you have a specific question, then
Yeah,
I might not have been able to follow it, I don't know. We did a lot of open and short circuit tests, right? Was this one a hard one? We even had a procedure, when we talked about the procedure, when we had the exam review, it was basically just do this over and over and over and over and over again. Yes, sir.
What's the purpose of the, all these steps again? Cause I do it, but like, I just go step by step, but I don't understand what it really is.
I'm gonna build you a real world transformer. I need you to give me RC, JXM. So I need a model of actual circuit model of the transformer. So I need to get those. And if you remember when we introduced this stuff, we actually looked at test reports, right, from a vendor that actually did the load loss and the no load test. So those are actual tests that they do so that you can validate, okay, or provide to the customer, here's what the impedances are of the transformer. Because what you learn about when you do power systems analysis, you buy a transformer that has, you know, a turns ratio and a power rating and yada, 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 a couple other things. But what happens when a fault occurs? How does a fault current go through the transformer? That's the type of information that's necessary. Any other comments or discussion on problem number 6? All right, let's go to 7 if I can get this to scroll up. Doesn't want to. If you remember the exam review, I actually talked about this. We have a current transformer, which has one turn of winding on one side, and then however many turns you need on the other side. It takes 1200 on this side and converts it to 5 amps on this side. The voltage drop across the load was 50 volts, right? So let's do the easiest one first. What's the power? 5 amps times 50 volts equals 250. You could either say VA or watts. I don't necessarily care. That's the power that draws from the primary side. Why? Because these transformers, we consider them lossless, right? Essentially no loss in power. So if you're delivering 5 amps to a 50 volt source, it's 250 watts. The other thing is, how do I get the voltage drop over here? Well, remember the turns ratio, I secondary to I primary is equal to 5 over 1200, right? That is equal to V primary over V secondary, correct? So V primary is equal to 5 over 1200 times V secondary. It's just a simple turns ratio problem. Yes, sir.
So the one own load wasn't, you didn't even use that.
You didn't need it.
So how is it delivering 5 amps
Because the voltage across it is 50 volts.
voltage across the load?
The load is 50 volts. Yep.
That means that it's delivering 50 watts, so it's drawing 50 watts.
No. No. Because I'm getting 5 amps through it, right? 5 amps. It's delivering rated current. And it's doing a 50 volt drop.
Oh, so the power draw from the load and then the power draw from the transformer is different?
Yeah.
Gotcha. Okay, that makes sense.
Go ahead.
That, the wording on that one confused me a little because when it said rated current, I wasn't sure whether or not to use 5 amps, but since it says 50 volts, I guess you're supposed to figure out the right current, but I think it would make more sense if you're like rated, or you said rated current for the load instead of rated current for the transformer, or something.
Yeah, the load is the load. The transformer is what's delivering rated.
But if it's I mean, the transformer has to be putting out more than 5 amps for a 1 amp, 1 ohm load via 50 volts.
Not- It's a current transformer. Yeah, you're talking about two entirely different elements.
Where's the other current for the,
There's losses in the transformer, right?
that's transformer, all transformers too.
It's stepping the current down, which means, right? That the voltage has to go up. So that's why it's 50 volts on the low side, and it's gonna be lower. It's 208 milliamps, yeah. Well, but so this is a perfect, so Aaron's bringing up a really good point. He put something wrong on the first, on his page. Just go back to, transformers are basically constant power devices. If you step down the current, you've got to step up the voltage. So you can easily see like, hey, wait a minute, if your voltage went from 50 volts to 10,000 volts, you're like, but the current went down, so how'd the power stay the same, right? So that's when you can sanity check your work. That's test number 1. General comments or questions? Too hard, too easy, just right? Read. Sort of, yes, but there's one person that didn't take the test, so I'm not exactly sure how to factor that in.
Give us an idea.
It was in the 60s, I think. There were a bunch of 80s, but there were some pretty low grades, and I'm not sure why. If you look at the grade distribution, they can't show you because you can see other people's grades, but it was skewed kind of on each side. Are you happy with your results or sad? Or in, but you were sad before? Well, how about I'm going to be magnanimous? You all want 15 points? Redo the test. For homework, redo the test. I would say let's just do the whole test because it won't take that much time to do the extra stuff and it'd be easier to grade. So if you want 15 points, redo the test and get the right answers and be clean and neat and orderly. If I have to hunt around, not a good thing.
So would you submit that?
I'll put a thing on Brightspace.
You upload a blank copy of that.
Yeah, I can do that.
And we won't get that until after the clock.
No, because they have to do a makeup test. So
Oh, really?
yeah, that's what I'm saying. So it's going to be, I don't know how to exactly grade it. So the question is, when do you want to do? Thursday? All right. So it's optional. Does everybody understand what that means? It will not negatively affect you if you do not do this. It can only positively help you. So if you redo the test and you want 15 more points, then you redo it. If you decide you don't want the opportunity to get the 15 points, it's totally up to you. It's not an additional assignment. Is that okay? Or getting a lot of confused looks? So it's just totally optional. You don't have to do it. Don't feel bad. It's totally up to you. Okay. All right. Any other questions, comments? Do you feel like you're prepared? Do you feel like seeing the test now makes some more sense? Do you feel like there was something that was completely foreign? The only one that I would say would be a little bit hard to think about was number 7, because that 1 ohm resistor kind of confuses people, but I'm like, it's just noise. Just think about the 5 and the 50. That's all you need. Because they don't agree, right? If you say, hey, wait a minute, how can there be 1 ohm and 5 and 50? It's like, well, I know what the voltage is and the current, so something had to disagree. So just go with what you know. And the other, you're gonna have losses in the transformer. Anything else? Usually this is your chance to say, hey, we should do this, we should do that, think about this, think about that. Or maybe I need to study differently, whatever. Those are just things to express this is your opportunity to express your opinion. Usually what happens after the test, a lot of people do this like, should have been able to do a lot better on it. So that's usually the case, but I don't know. Is that how you all feel? Or do you feel like, nope, I want to, I could do it any better?
I think I had trouble going between like three-phase and single phase.
Yeah, I'll
That-
keep like,
Yeah.
yeah, like I went over the homework and there's a lot of single phase.
Yeah,
And then the exam was like a lot single phase, so that's for, that kind of feeling out.
Okay, fair. We can do more practice with stuff. I tried to simplify it down though with three phase or single phase. It's just three, right? Multiply by three or divide by three.
I don't think I mixed up on another end, to multiply by three, divide by three, multiply by the square root of three, and divide by the square root of three.
Yeah, unless it's a phasor, right? It's always going to be three. Everything else is square. Everything else is three. Even if you look at this equation over here, the S equals square root of three, V line, I line, conjugate. That's really based from this equation. We just sneak in the fact that V line equals square root of three V phase, and I line may or may not equal square root of three I phase. You're going to have one or the other. You won't have both. And so what we do is we substitute, we start substituting into here, and that's how we end up with a square root of three. But that's the only time when you have a square root of three, but it's really because of the substitution. Okay. So remember, that's optional to do the test. But the other thing too is like, I'd like to see the average be a little bit higher. And I have a philosophy. I don't give anything. You're earning them, right? Points. So I don't want to give you points. That feels cheap. But you're earning them by doing a little bit of extra work. How does that feel better? Just scaling things? Do you feel like, oh yeah, I feel like I'm doing it. And you hopefully will learn the material a little bit better. But I forgot to tell you, I'm not going to post the video or the presentation stuff. Okay, I'll post the video and that in the test. So you'll have access to all three. That would be really unfair if I didn't do that, but I'll post all three. Humor's not working on me. Oh, I get it. That's bad. All right, so like I said, I try not to push too much material, so we have a bunch of time, but you can start on the test or read it earlier if you want. And that's it. Anybody in TV land have a question or?
Nope, good here.
All right. All right, thanks, everybody. Have a great day. Take care.
Thanks, Paul. This was helpful.
Yep, thanks, Joe. Have a great day.